How was your test? Average. Okay. I'll go through the solution of my part. Okay. So do you want the solution? Okay. Is the screen visible to you all? Okay. So my part of questions are from, so you can unmute yourself wherever you find any doubt. Okay. Is from here onwards. Question number 21. Okay. So the valid instruction or instructions in isolated IO. So isolated IO is same as that of IO mapped IO. So we are having two ways to interface an IO device with the processor. Either it can be a memory mapped IO, where or it can be used as an IO mapped IO, or it is also known as an isolated IO. So in case of isolated IO, the only instructions which are used to interact with the IO device, or which are used to communicate with the IO device is by using in as well as out instruction. Okay. So in case of in instruction, in or out instruction, the default registers, register where you can, which is used as where you can get the data, or where from where you can transfer the data, is the AL or AX register. If it is an 8-bit port, or if it is an 8-bit port, then we can use it as an AL register. Whereas if it is an 16-bit port, then it is used as a it can be transferred through AX register. Fine. So here in case of memory mapped IO, you can use this move instruction, or add instruction, or AND instruction. Any of these memory related instructions can be used only in memory mapped IO. Whereas in case of isolated IO, you can use the in instruction as well as out instruction. So you can see that if I'm using this, this is a valid instruction. Out, the AX registers value to this 8-bit port address, that is 3D. Okay. And if I'm using a 16-bit port address, then the default register which is used as a port address is the DX register. You cannot use any other register. Okay, the DX register is a default register. So you can see that in this instruction, in AX comma within the bracket DX, so this is a valid instruction because the 16-bit address, port address, is provided into the DX register. Whereas this is not valid since it is using a port address into as a in the BX register. Hope everyone is clear. So move, add, and etc. This cannot be used for isolated IO. This is also, this can also be not, this instruction may not, even it cannot be used, as here it is directly providing the 16-bit port address. As I said, if we are using a 16-bit port address, then by default that port address should be into the DX register. Hope you are, everyone is clear with this. Okay, so this was the first question. Then the type of data transfer shown in this figure is, you can see that a strobe signal is given by the transmitter, okay, saying that the data is ready to be I have placed, I'm going to place a valid data. So in response to this strobe signal, the receiver will send an acknowledgement signal saying that now I am ready to get the data. Once this acknowledgement is received by the transmitter, then it will start transferring the data. So this thing would be carried out in double handshake. Are you getting this? In case of single handshake, as the strobe signal is provided, as well as the data is also placed onto the bus. Okay. Whereas in case of double handshake, first it will take consent from the other end, asking whether it is ready to accept the data. Okay. If it is so, then it will start transferring the data. So this is an example of a double handshake signal. Hope this is clear, everyone. Okay. The third one is for transferring the data from one computer to the other computer. The type of parallel data transfer is what? Okay. So we are trying to transfer the data from one computer to the other computer. So in this case, we need to check whether the other end is ready to get the to accept the data. Okay. So here also, once we get the once the transmitter gets the acknowledgement from the other end, it will start transferring the data, and hence this one is also, I mean, the data transfer from between two computers is also a double handshake IO. Okay. Is it clear? Why is it a double handshake IO? Okay. If the reset pin of 8255 are set, okay, if it is made high, then what happens? So all the port pins are made it as an input. They are considered to be in the input mode. This is because if it is if it is set to the in the output mode, what happens? Whatever some random data or some random value might be present into the port buffer, and it would start transmitting to the other end. Whereas the receiver, which the device which is connected to that port, it may not be the I mean the device which would get the it is not the device where which receives the data. Okay, it is not, it might be an input device or it might be an output device. Okay, so by making this 8255 in all, if as soon as it is reset, then all the port pins are made, they are by default they are made to as an input mode. Okay, then this is wrong because it is not set to output mode. If it is so, the device which is connected to the port might be damaged. Then the CS and IP is set to this. This is wrong. This is because the third option, it is valid for the reset pin set to the 8086, not to 8255. Okay, if the 8086 reset pin is made high, or if it is set, then the CS and IP value would be FFFF as well as FF as well as 0000. Okay, this you all are aware. Then dashboard pins can be used as handshake signal. So this is a bit simple. You know that port C pins can be used as an handshake signals. Then this one. So the address of the control register in the given diagram of 8255, this is the 8255 dash is dash, and the mode of operation of port A. So these are the port A pins and these are the port B pins. So this is some switch which is connected to this port B, and this is the port A which is connected to some LEDs. So what mode of operation should be there for port A and port B? It has been asked. So can you tell me what would be the port address here? Here it is given, it is for the control register. So as we know that there are A1, A0 pin is of the 8255. This would decide whether it is a these two bits would decide whether we are addressing for port A, port B, port C, or the control register. So if A1 A0 pin is 1 1, then it implies that we are referring to the control register. Do you agree to this, all of you? Okay, so we have to find out what would be the address for the control register. So for this, you can see that A15 to A8 pins are there, and A15 to A15, A60, A15, A14, A13, A12, as well as A11. So all these when are should be zeros. Then only, since it is connected through the inverter, that means it would become 1, and all these three are 1. So what does it mean? As we know that this is a NAND gate, if all the inputs to this NAND gates are 1, then this output of the NAND gate would be 0. Do you agree to this? So here the address lines would be 15, 14, 13, 12 should be 0, 0, 0, 0. This 11, 10, 11 should be 0, 10, 9, 8 should be 1. So 0, 0, 0, 0, 0, that is 0, 0, 1, 1, 1 is 7. Okay, then this should be 0, A7 bit should be 0. Okay, so that should be this indicates 0, then 1, then this is 0, 0, 0, 1, 0, 0 is 4, then A3 should be 0, then A2, A1 should be 1, 1, because we want to select the control register, and A0 should also be 0. So 0, 1, 1, 0. So that would be 6. Okay, so here I'll have 0, 7, 4, 6 should be would be my address of the control register. And port A, so here we don't we are not using any of the these ports in the handshake mode. Then what should be the mode of these ports, port A as well as port B? What should be the port address? Sorry, not port address, mode of the port. IO port, that is fine. It should be in mode 0, because we are not having any of them are providing the handshake signals, or they are using the handshake signals. So port A as well as port B, they should be in mode 0, as well as port B should be in the input mode, whereas the port A should be in the output mode. But here it is said what is the mode of operation. So both these are in the mode 0. So port A is also in mode 0 and port B is also mode 0. So this 0746, 0, 0, 0, 0. So that is the correct answer. Hello, is this thing clear, everyone? Okay. Now, this part, the data in the AL register at the end of the given code. So this is the given code. So what should be the data at the end of this program, that we have to find it out. So here, MoveAX, this we are having some lookup table, tab defined by 536, some data is given here. So the SI register is initialized with data 1. BX register is initialized with the offset value of this tab, this lookup table. Okay, so this offset value of this is loaded into the BX register. Then AL register is initialized with 6. After this, we have used this XLATB instruction. What does it indicate, XLATB instruction? XLATB. XLAT is used for as a translate instruction. So the BX plus AL register. So BX register contains the offset value into the data segment of that lookup table, plus the AL register. So AL register contains the displacement of in the lookup table. So you can see that BX is pointing to this offset value of this 5. Okay, so then it has to be summed with 6. So 0, 1, 2, 3, 4, 5, as well as 6. So this would be the and this value, that is 0F, would now be copied into the AL register. Okay, so at the end of this program, the AL register would have the value as 0F. Is it clear, everyone? How about others? Okay. A 32 KB of RAM is to be interfaced to an 8086 processor. Okay. The first address of the RAM is, it is given as it is 48000H. This is the first address. And the entire range, what is the entire range of the memory which is addressed by this 32 KB RAM which is connected? And we have to find out what are the address lines, which address lines are connected to the chip select line. Okay, that we have to find it out. So for this, as we are having 32 kilobyte, so what do you mean, how many address lines would be required to address this 32 kilobyte? It should be 15. Okay, so 15 address lines are required. So as we know that the lower order, this 0, each number indicates one hex number, isn't it? So, and one hex number it corresponds to 4 bits. So 4 bits for this, 4 bits for this, 4 more bits. So 12 bits have been gone. The lower order 000 corresponds to 12 bits. And this is what? 1 followed by 3 zeros. So the among, in this 8, the rest of, in this 8, it is 8 can be represented as 1 followed by 3 zeros. So those 3 zeros plus these 12 bits, it would indicate 15 bits. So the starting address of that is 48000 and the ending address. So in the memory range, the ending address would be always all ones. Okay, so what would be the last address in that case? 4 1 1, yes, 4FFFFF. Fine. So that would be the last address into this memory range, 480000 till 4FFFF. Now, so 15 bits have been used. So that means A0 to A14 would be used to address each of the memory location of this 32 KB RAM. Whereas the remaining address lines, that is 15 to 19, can be used as a chip select. Okay, so A15 to A19, so remaining address lines A15 to A19 can be used as a chip select line. Is this thing clear, everyone? Okay. So the next question is, which of the addresses in the given figure of memory interface is or are valid addresses? So this is an example of a linear encoding. Okay, so here the chip select line of this memory is connected to the A18 pin of the address line. Fine. So this A18 pin, when it is 0, then these two RAM would be selected. Do you agree to this, all of you? A18 is connected to that, and when A18 pin is 0, okay, because it is CS bar, here it is CS bar, that means when this pin is low, then these two ICs would be selected. Okay, so I have to find out among these list of addresses whatever is provided, where the A18 pin is low. Okay, so for example, if I take this the first example, that is 7, I have to consider only the first 4 higher order 4 bits, because A18 comes under higher order 4 bits. So in case of 7, the second bit indicates 1. Okay, that means this is not a valid address to select that particular RAM. Are you getting this? We have to select A18 bit. So A18 comes under the higher order 4 bits. Okay, because the higher order 4 bit corresponds to A19, A18, A17 as well as A16. So here, if I represent 7, it would be 0, 1, 1, 1. So since the A18 pin is 1, this is not a valid address. How about this? 3CFF, 3 corresponds to 0011. So that means A18 bit is 0 here. So this is a valid address. 2 is also a valid address because it is 0010. How about A? A corresponds to 1010. So here also A18 line is A18 pin is 0. Hello, are you getting me? 10 A corresponds to 1010, and hence the second bit is 0 here. Then comes 9. How about 9? It corresponds to 1001. So that here also the A18 pin is low. So this is also a valid instruction. C corresponds to 12. 12 is nothing but 1100, isn't it? So 1100. So A18 pin is high here. So this is not a valid address. Similarly, the last one, 4800, 48005. 4 corresponds to 0100. So this is also not a valid address. Hope this is clear. You have to check the A18 bit which is 0. If it is 0, then it is a valid address. Is this thing clear, everyone? Hello? Consider an 8086 based system with 2 chips of 64 KB ROM. So here we are having 2 chips of 64 kilobyte of ROM. So the total memory capacity would be 128 kilobyte of RAM and 2 chips of 32 KB of RAM. That means the total capacity of RAM is 64 kilobyte. Select the starting of the EEPROM suitably. So what should be the address of the EEPROM? Here it is not explicitly given. If it is not explicitly given, what should be the address of the EEPROM? FFFF would be the ending address. As we know that FFFF0, that is the address while we reset the processor, and that contains some program, okay, and that program should be resided into the ROM, isn't it? If it is in the RAM, that program would be lost. So that should be resided into the ROM, and hence FFFF0 should be the ROM address. Okay, if it is mentioned here specifically, then you can use that address. But if it is asked to suitably, you have to use the address. Then you have to use that FFFF0 should be the ROM address. Followed? So the size of the ROM is 128 kilobyte because there are 2 such chips. So to address this 128 kilobyte, how many bits would be required? How many bits would be required for addressing 128 kilobyte? 17 bits. Fine. So A0 to A16 are meant for the addressing of the ROM. Okay, the how many bits are left now? 17, 18 as well as 19. 3 bits are left. So as we know that the ending address is FFFFF. Okay. So among this FFFFF, the higher order 3 bits should be 1. So that was the ending address of the ROM. The starting address ROM, for the starting address of the ROM, the higher order 3 bits, that is 19, 18 as well as 17, it should be 1, whereas the rest of all should be zeros. So what should be the starting address in that case? E0000. Very good, very good. Okay, that would be the starting address. So here E0000 is the starting address, and the last address is FFFF. Now, the starting. So this is for the ROM, and for the RAM, the starting address and ending address of RAM is so. The RAM address should be continuous. It is said that the RAM address should be continuous. So what should be the, if this is the starting address of the ROM, and if I want the addresses should be continuous, what should be the last address of the RAM? 1 less than this starting address. So E00000 minus 1. So that is DFFFF. Very good. Okay. So DFFFF would be my ending address, and accordingly I have to find out the starting address. So the total capacity of the RAM is 64 kilobytes because there are two such chips. So to address the 64 kilobyte of RAM, we require 16 bits. Okay. So A0 to A15. So that is meant for addressing of the RAM, whereas remaining 16, 17, 18, 19, those 4 bits are as it is. So this D would be, the higher order 4 bits would be as it is. So this D would be as it is, whereas the remaining 16 bits. So this is my remaining 16 bits. So all of them are made 0. So this is the correct option. E0000 to FFFF, that is for ROM, and D000 would be the starting address of RAM, and the ending address of the RAM would be DFFFF. Hope this is clear, everyone. Okay. So 8255 is interfaced with 8086 processor. A keyboard is connected at port B. Okay. So if I'm connecting a keyboard to any port, so in which mode it should be? Input mode. And the mode number? Mode 0, mode 1. Yes, it is mode 1. If it should be in the mode 1, because once the key is pressed, a strobe signal would be sent. Okay, by looking at the strobe signal, the 8255 will access the data. So that we have already learned. Okay, so whereas the port A is, we are not using this port A, so it can be don't care. Port C upper can also be a don't care. Okay, whereas port C lower, it should be in the input mode, whereas port B should be in mode 1 and port B should also be in the input mode. So the lower order 3 bits should be 1, and the most significant bit of the control word should also be 1. So whereas rest of all can be don't cares. So lower order 3 bits, that means 7 as well as F. These two are the valid one. Okay, and the higher order 1 bit should also be 1. So these two are the valid control word for the given for this given description, whatever is given. Okay, hope everyone is clear. If it is in the input mode, that bit should be made 1. If it is in the output mode, it would be 0. Okay, and since we are using port B, so as we know that the lower order 3 bits are meant for port B, mode of the port B. Port B, whether it is in the input or output, it is used as an input or output port, as well as the lower order, the least significant bit is meant for the port C's lower order 4 bit. Okay, and as we know that for port B, port C's lower 4 bits are used for the handshake. So even port C's lower 4 bits can be used as an input port. Hope everyone is clear. Okay, so this is a solution from my part of the paper. Any doubts in this still? Everyone is clear with these things? Hello? Was the paper tough now? Okay then. Hope everyone is clear with the things. We'll continue with the next topic of our course. Is the screen visible to you all? So till now we have learned about the code segment, data segment, as well as extra segment, how it is used, etc. We have learned. So from today onwards, we'll see how to use the stack, where it is used, and how to declare the stack segment, because it is a bit different than that of the declaration of the other two, that is data segment or uh, extra segment. It is somewhat different. So how to work with the stack and how it is used in the procedures that we'll see. Okay, one by one. The stack segment of a program is used to temporarily storage of data and addresses. So here we can also store, apart from storing the data, we can also store the addresses. So can you give me one example where we store the address into the stack? Can you give me any example where we store the address into the stack? In jump instruction, we don't store the return address. In the function call, very good. Okay. So while we call the function, the return address should be stored into the stack. Okay. There should be some way in which we can store the return address, so that while we finish the function and while it returns back to the main program, it should come to know where it has stopped and from where it has to continue. Okay. And hence that address should be stored into the stack. Even it might be possible that while we are performing any operation, sometimes the data can be stored temporarily, because the number of registers what we have in any of the system are limited, isn't it? We are having only 4 general purpose register. So if those registers are already occupied for while we are writing any program, and if I want to reuse those registers, then the content of the registers can be temporarily stored into the stack. Okay. And then as soon as that register become free, we can get it from the stack. Fine. A stack is a one dimensional data structure, and it is uh, the items are stored in the last in first out manner. Okay. The item which is lastly stored into the stack would be first popped out, or first it would be retrieved from the stack. And whereas in queues usually it would be first in first out, but in the stack it would be last in first out manner. Follow? And always there is a top of the stack. It is a last addition to the stack. So whenever we are putting the data onto the stack, the top of the stack would change. Okay. And the data always is placed at the top of the stack, and that top of the stack is the last addition of the stack. So once we have pushed, once we have placed the data, the top of the stack would change. And now once again, if I am placing the data onto the stack, then it would be the last addition of the stack. The stack segment, so for the base address of the stack is provided into a register which is known as a stack segment register. As we have the data segment register, the code segment register, the extra segment register, which contains the base address of any of the segment. Similarly, the SS register, which is also known as a stack segment register, it contains the base address of the stack. It contains the segment number of the stack segment, or base address of the stack is provided into the SS register. Now, the complete 20-bit address of the memory or the stack, we can get it from the base address would be in the SS register, and the default register which acts as an offset value, it is provided into the stack pointer. So usually the stack pointer would it is always pointing to the top of the stack. So this SS:SP forms the complete 20-bit address. You know how to get the 20-bit address. And the one more register which can be used with the stack is, apart from SP, we can also use the register like BP, that is the base pointer register. Okay. So A stack segment register can be accompanied with either SP or BP register. Whereas you might have learned that DI register, if I'm using a string instruction, then it is accompanied with which segment register? Hello. If I'm having a DI register, it would be ES register, isn't it? So this is a default register, as we know. Whenever I'm using DI register, then extra segment register should be used as a default segment register. Similarly, while we are using SP or BP register, the default segment register would be the stack segment register. Initially, before any data or address have been placed onto the stack, the SP contains the offset address of the memory location immediately following the stack segment. So this we have already discussed. So how this stack would be implemented, let us see. See, the base address of, so assume that this is my stack, blue colored box is my stack. The base address of the stack is provided or it is indicated by SS register, and the stack pointer is pointing to the top of the stack. So this is the top of the stack. Follow? Now, whenever some data is pushed onto the stack, okay, so the stack grows in this direction. Whenever the data is placed onto the stack pointer value would be decremented, and the data is placed onto this into this memory location. So the stack grows in this direction. You can see that this is a blue colored arrow mark, and it grows in this direction. Fine. And say suppose these memories are already in use, then the stack SS colon SP or the stack pointer is pointing at this particular address. Here it is pointing. So one more data, if it is placed onto the stack, then this memory would also be in use, and it would the SP stack pointer would be pointing at this particular address. Are you getting this? Hello. Stack pointer would always be pointing to the top of the stack. Say suppose I'm having a 100 byte stack segment. Okay, I have already allocated a 100 byte of memory as a stack segment. So the base address of that stack segment is provided into the SS register, and my stack pointer would be pointing to the 100th memory location. Are you getting this? Say suppose this is my 0th address and this is my 99 address, if I'm talking about decimal address. So the stack pointer would be at the top of the stack, that is at the 100th address. Have you understood now? When we put some data onto the stack pointer value would be decremented. Getting all of you? Say suppose currently the stack pointer is pointing to this memory location, and one more data is pushed onto the stack, then the stack pointer would be pointing at this address. At this address it would be pointing. Are you getting this, all of you? Okay. So the stack segment, say suppose I am keeping aside 100 bytes of memory as a stack segment. Are you getting me? Okay. So the base address of that memory is provided to the SS register. Fine. I say suppose 0th memory location is pointed by the SS register, and 100th memory location is pointed by the SP register, stack pointer register. Now when some data is placed onto the stack pointer value would be decremented. Currently SP is pointing to the 99th memory location. Now one data has been pushed, so stack pointer would be decremented. Now it might be pointing to the 98th memory location. Say suppose one more data is placed. Now it would be pushed onto the stack, and it is pointing at the 97th memory location, and so on. So the stack pointer would be decremented as the data is placed into the stack. Hope this is clear, everyone. We'll see how it is used in our 8086 processor as we go further with some instruction. Say now there are two more instructions to put the data on or to retrieve the data into the stack or from the stack. The very first instruction is push instruction. Okay, so push instruction adds a new word onto the stack. So that means if I want to place some data onto the stack, I have to use this push instruction. So push, the syntax is something like this: push the source. Now the source can be it can be either the 16-bit register or it can be a memory, but of type word. You cannot push 8-bit register value. You cannot, I cannot use push AL or push BL or something like that. Okay, so the source should be of 16-bit register or it can be a memory word. For example, you can see that if I use the example is push AX, so that means the AX register's value would be placed onto the stack. Okay, similarly we can also push the segment registers value also. So here you can see that we are having this value as push DS. That means the data segment registers value, we are pushing it onto the stack. Okay, whereas this is one more example in which memory's value would be pushed onto the stack. For example, here push word pointer within the bracket SI. That means whatever is the data at the address DS:SI, okay, so that 16-bit data would be pushed into the stack segment. Is it clear? These are some of the examples, valid examples for the push instruction. So how this push instruction would work, we'll see. It causes the stack pointer to be decremented by 2. First, what happens whenever if I write if I use the push instruction, the very first step what it will do is the stack pointer value would be decremented by 2. Here SP value is decremented by 2 because we are pushing a word, not a byte. So if I am pushing a word or if I am placing a word, that means 16-bit data, and since we are having the word size of the memory as only 8 bits, 2 memory locations would be required to place the 16-bit value, and hence the stack pointer would be decremented by 2 first. Are you getting this? You may ask, why is the stack pointer is decremented by 2 and why not by 1? Since we are pushing a word size data, not a byte size data, and hence we require 2 memory locations to push the data, to place the data onto the stack, and hence the stack pointer would be decremented by 2. So push instruction causes the stack pointer to be decremented by 2. Then a copy of the value in the source, so whatever is there into the source is placed in the address specified by the SS:SP. Okay, so since the push instruction decrements the stack pointer by 2, you can see that it is filled a word at a time backwards from the last available word. So you can see that here it is pushing, it is placing the data in, you can see that the stack is growing in this order. You are not, the stack is not growing from the lower address towards the higher address. Are you getting me, all of you? Okay, so this is how the push instructions would work. So this is an example which shows how the push instruction would work. So suppose if I am using the instruction like push BX, okay, in that case, and let the BX register is having the value as 6AB3, okay. The stack segment SS register is having the value as 0300. This is the base address, and this is the stack pointer is pointing to this address. That means this is the top of the stack. Currently the stack pointer is pointing at this particular address. So you can see that the base address is 0300, and you know that the lower order 4 bits should be 0 here. So the stack starts at the address 03000. Now since it is push BX and stack pointer is pointing to this address, that is 03800. You know that how to find out the physical address. 0300 0 plus 0800. So that gives the address as 03800. So currently the stack pointer is pointing at this address. Okay. And when we have this push BX instruction, which contains the 6AB3, the higher order 8 bits, that is 6A, is placed at this address, that is 037FF. lesser than this, and the lower order 8 bit, that is B3, it is placed at this address, that is 037FE. So the 2 bytes of the data is placed onto the stack here. Now the new value of the stack, it is pointing at this address, that is 037FE. Hope you have understood. Currently the stack pointer is pointing at this address, that is 03800. When we are having a push instruction, push BX, so what we have learned, whenever we have a push instruction, first the stack pointer would be decremented by 2. So the 03800 minus 2 would result to 037FE. Do you agree to this, all of you? And then the 16-bit data would be placed in this manner. 6A is stored at 037FF and B3 is stored at 037FE. Any doubts in this? This is how 16-bit data would be placed. Say suppose now I am using push AX. After this, push AX instruction is used. And assume that AX has 1, 2, 3, 4 values. So where that 1, 2 and 3, 4 would be placed? Where the 1, 2 would be placed? What happens first? If the processor finds it is push AX, what it will do? The stack pointer would be decremented by 2. So currently the stack pointer is having this value 037FE. Okay, decremented by 2. That means it is 037FC. Do you agree to this, all of you? Then 3, 4 is placed at the lower address and 1, 2 is placed at the higher address. Very good. Okay, hope everyone is clear with this. Okay, this is how the push instruction would work. So you can see that the stack grows in this direction. Okay, initially the stack pointer is pointing to the 03 to the maximum address, and then the stack grows in this direction. Follow? The next instruction is a pop instruction. Push instruction would place the data onto the stack. The pop instruction would retrieve the data from the stack. Okay, so pop instruction removes the last word placed onto the stack. Pop destination, and as we have in the push instruction, the source can be a 16-bit register or a memory word. Similarly, the destination can also be a 16-bit register or a memory word. So pop instruction causes the content of SS:SP to be moved to the destination field, and after the data is copied into the destination, the stack pointer is incremented by 2. Whereas in push instruction, before placing the data onto the stack pointer was decremented by 2, and then it would be the data is placed. Whereas in pop instruction, first the data is retrieved from the stack, and then the stack pointer is incremented by 2. Are you all comfortable with this? Understood the things? Okay. So push and pop works only with words that we have already discussed. You can only transfer or you can store 16-bit data, not 8-bit data. Byte and immediate words byte and immediate data operands are illegal. I cannot write push 1, 2, 3, 4. You cannot push 1, 2, 3, 4 onto the stack. Okay, so the source or the destination can only be either register or the memory. It cannot be either the 8-bit data, or it cannot neither it can be an immediate data. Is it clear? So the example of this pop instruction is pop AX. That means the top of the stack, whatever is there, that would be the popped into the AX register. You can also pop it into the segment register like CS or DS or any other register, or you can copy the data whatever is at the top of the stack to the memory which is pointed by DI register, DS:DI. Is it clear, everyone? This is how the pop instruction would work. So you can see that if I'm having currently say stack segment is the base address of the stack segment is all zeros, and currently the stack pointer is at this address 1006. Okay, now if I'm having a pop BX instruction, Okay, and at the top of the stack, I'm having 3, 9 as well as 2F. So if it is a pop instruction, whatever is the data currently into the memory, that is 392F, it would be copied into the destination which is specified with the pop instruction, that is BX. So 392F is copied. After that, the stack pointer would be incremented by 2. So currently it was 1006. Now it would become 1008. Hope everyone is clear with this. Okay. So first the data is popped from the stack, and then the stack pointer would be incremented by 2. So as we have push and pop instruction for the registers as well as for the memory, we can also have we also have a flag register. Say suppose while we are using some procedure, it might be possible that the status of the flag would vary. Okay, it might be varied by the procedure. And if I want to while I return from the procedure, I want my flags to be intact, as uh, the it should not be changed. So for that, I have to store the status of the flag into some memory location. Okay, so we can use these instructions like push and pop, push F as well as pop F instruction, to push the current value of flag register onto the stack, as well as to pop the current value of the whatever is there at the top of the stack can also be popped. Hello, is this thing clear? The difference between push as well as push F. Push F, F means flag register. So here this is, I cannot write push space flag. Okay, so for that I can use push F as well as pop F instruction. Push copies the contents of the flag register onto the stack, and it has no operands. I cannot write push F space flag. Okay, if I write push F, it is by default that flag register's value would be copied onto the stack. Then comes pop F instruction, in which whatever is the top of the stack would be retrieved into the flag register. Okay, push pop and push F do not affect the flag. So all these instructions, whatever we have discussed till now, these are the push and pop instructions are data transfer instructions. And as we know that no data transfer instruction would affect any of the flag register. And POPF could theoretically change all the flags because it resets the flag register to some original value that you have previously saved with the pushf instruction. So that's what I have said. So if I want to, if I am calling a procedure, then the status of the main program would be lost, isn't it? So if I want to keep my, while I come back, if I want to have my status of the main program into the flag register, for that I can push it into the stack by using this pushf instruction, and we can retrieve it back using this popf instruction. So you may ask, you may tell that if I'm using popf instruction, it might be possible that the status of the flag would change, but this status of the flag which we have already pushed, that we are retrieving it back. So that's why theoretically we can say that it would not change the status of the flag register. Okay, so we'll stop here and we'll continue in the next lecture. Any doubts here?